Good morning. This is the second lecture on axial flow turbine. The contents of the lecture are degree of reaction for an axial flow turbine. Thus, I've discussed on introduction and velocity triangle, impulse turbine, reaction turbine, relation between xi, phi, and r. To initiate the discussion on degree of reaction of a gas turbine, I presented here the schematic of a stage, which consists of a nozzle denoted by N and a rotor blade designated by R. Station 1 represents the inlet to the nozzle, where 2 indicates the exit from the nozzle and entry to the rotor, and the station 3 indicates the exit from the rotor. Now, with respect to this figure, what happens? The flow is expanded as it passes to a turbine stage. The degree of reaction, or simply the reaction, is a useful dimensionless parameter and is denoted by the symbol R. It may be defined for a turbine as the fraction of overall enthalpy drop or pressure drop occurring in the rotor. Thus, R can be stated as H2 minus H3 divided by H01 minus H03. So thus, it is the ratio of enthalpy drop in the rotor by enthalpy drop to the stage. Now, if we consider the Cp is constant, this can be written as R is equal to T2 minus T3 divided by T01 minus T03. Thus, it is the ratio of static temperature drop in the rotor to the total temperature drop in the stage. Further, turbine stage in which the entire pressure drop occurs in the nozzle is called an impulse stage. Thus, here I have defined the impulse stage and the reaction stage. Thus, please note that in impulse stage, the total pressure drop will occur in the nozzle and there will be no pressure drop in the rotor. Thus, I have written here the entire pressure drop occur in the nozzle for an impulse turbine. Similarly, for a reaction stage, the portion of pressure drops occurs in the nozzle and the rest occurs in the rotor. Thus, I have defined the reaction stage as the stages in which a portion of pressure drop occurs in the nozzle and the rest in the rotor are called the reaction stage. Thus, following the definition, what is a 50% reaction turbine? In a 50% reaction turbine, the enthalpy drop in the rotor would be half of the total enthalpy drop in the stage. Thus, please note that here I have defined degree of reaction and then I have defined an impulse stage versus reaction stage. Following the definition of an impulse stage, I have presented here the velocity triangle. If we take a circumferential section and stretch on a paper, I would get the velocity profile of an impulse turbine stage. Here I have indicated the nozzle followed by the rotor. Please note the rotor constructions. It is very symmetrical blade. As per the definition, the entire pressure will drop in the nozzle and it would create a jet of high speed, which has been indicated by C2 here, that C2 makes an angle alpha 2 with the z-axis. Now, the relative velocity W2 will enter the blade at an angle beta 2 and it will leave the blade at an angle beta 3, where the magnitude I have indicated here as W3, and U is the blade speed. Now, since there will be no pressure drop occurring in the rotor, W2 in magnitude must be equal to W3, and thus beta 2 in magnitude must be equal to beta 3. Following this, we can draw the velocity triangle, and both inlet and exit velocity triangle, inlet to the rotor and exit from the rotor, have been superimposed here, where I have presented W2 U would result in C2. C2 makes an angle alpha 2 and W2 makes an angle beta 2 with the z-axis. Please note the magnitude of C2. It's very high. Now, W2 and W3, they are equal in magnitude. So I have drawn here the exit velocity triangle. W3 U is equal to C3. C3 makes an angle alpha 3 with the z-axis, and W2 makes an angle beta 2 with the z-axis. Note here W2 and W3, they are equal, and thus beta 2 and beta 3, but they are opposite in sense. Cz be the axial velocity within the stage, and Cz would remain approximately constant as it flows to the stage. Furthermore, W theta 2 C W theta 3 and hence C theta 2 and C theta 3 are the tangential components of W2, W3, C3 and C2. Note that W theta 2, C theta 2 and C theta 3 all are in the direction of U are considered positive, but W theta 3 are in the opposite direction of U and hence would consider negative. Hence, with this, I have explained the velocity triangle of an impulse turbine, where the characteristics are to be noted that W2 and W3, they are equal in magnitude, and thus beta 2 and beta 3. C2 will be in high in magnitude, since the entire pressure drop occurs in the nozzle and there will be no pressure drop occurring in the rotor. Now I'll derive the expression for blade loading capacity of an impulse turbine following the velocity triangle and try to establish the influence of nozzle exit angle for work transfer. I have indicated here again the velocity triangle of an impulse stage. Now it can be stated that since no enthalpy change occurs within the rotor, magnitude of W2 should be equal to magnitude of W3. If the actual velocity is x held constant, then we have beta 3 is equal to minus beta 2. Now, following the velocity triangle, we can say w theta 3 is equal to minus w theta 2, since w2 is equal to w3 and beta 2 is equal to beta 3 in magnitude, but they are opposite in direction. Hence del c theta, that is equal to c theta 2 minus c theta 3, would be equal to twice w theta. Again, w theta can be expressed as c theta 2 minus u. Thus, I can write del c theta, that is equal to c theta 2 minus c theta 3, would be equal to twice within bracket c theta 2 minus u. Using the velocity triangle, I can write c theta 2 in terms of alpha 2. So it would be twice u within bracket cz by u tan alpha 2 minus 1. Now, by definition, xi, which is the blade loading capacity, is equal to c theta 2 minus c theta t divided by u. Thus, xi becomes twice within bracket phi tan alpha 2 minus 1. Just for an impulse turbine, I have got an important relation, which is equal to xi is equal to twice within bracket phi is the flow coefficient tan alpha 2 minus 1, where xi is called blade loading capacity. Here I would like to say that the equation 7, which is xi is equal to twice within bracket phi tan alpha 2 minus 1, illustrates the effect of nozzle outlet angle on the work output of an impulse turbine. It is evident that the nozzle angle should be as large as possible for large power output. Please note that two difficulties are associated with very large alpha 2. What are these difficulties? I have stated here. For reasonable axial velocities, that is, the reasonable flow per unit frontal area, it is evident that large alpha 2 creates very large absolute velocity and thus the relative velocities throughout the stage. Now, high losses are associated with such large velocities, particularly if the relative velocity W2 is supersonic. If W2 is supersonic, there will be complex shocks within the rotor that involves very high losses. In practice, losses seems to be minimized for the value of alpha 2 around 70 degrees. In design of an impulse turbine, we do not allow alpha 2 beyond 70 degrees. Now I'd like to introduce a special case where let us consider Cz remains constant. Furthermore, if we assume the exhaust velocity becomes axial, then c theta 3 must be equal to 0. And if c theta 3 is 0, then we can prove c theta 2 is equal to twice u. Now please note that if c theta 3 is 0, that is exhaust becomes axial, then here look, if C3 becomes axial, then C3 will have minimum values. Now C3 is associated with the kinetic energy of gases leaving the stage. Hence, the stage efficiency would be maximum for a exhaust which is normal to U, that is axial exhaust. Thus, I have C3 becomes axial, c theta 2 would be equal to 2 twice u, and hence the equation 7 becomes psi is equal to 2. You can easily prove for this case value of alpha 2 would be equal to c theta 2 divided by cz, that is equal to twice u by cz equal to twice by 5, and hence psi becomes 2. Thus, I have indicated another thing, that for a normal exhaust or for an axial exhaust, psi is equal to 2 for an impulse turbine. Now for a given power output and rotor speed and for a given peak temperature, the equation 7 is sufficient to determine the approximate mean blade speed, that is the mean radius of a single stage impulse turbine having axial exhaust velocity. Now, if the blade speed is too high or the mean diameter is too large, it is necessary to employ a multi-stage turbine for stress limitation, in which each stage does part of the work. Now I'll discuss about reaction turbine. I'll take an example of 50% reaction stage where the blading are symmetrical. Hence, for a 50% reaction stage, static enthalpy rise in stator must be seen as that of the rotor, and thereby the kinetic energy change relative to each blade row would be the same. Now figure 6 illustrates the velocity triangle for a 50% reaction machines. I'll derive here the blade loading capacity of a 50% reaction turbine. Please note the aerofoil sections, the construction of the nozzle and that of the rotor for a 50% reaction turbine, where the blading for the nozzle are the same for the rotor, however their orientation are different. Let us consider C2 be the exit velocity of the nozzle that makes an angle alpha 2 with the z-axis. Similarly, W2 be the inlet relative velocity to the rotor that makes an angle beta 2, and W3 be the exit velocity of the rotor which makes an angle beta 3 with the z-axis. In 50% reaction machines, since the pressure drop also occurs in the rotor, thereby W3 would be more than that of W2. U be the blade speed as before. Now let me draw the velocity triangle here, where both the inlet and the exit velocity triangle I have superimposed. So inlet velocity triangle is represented here by W2 plus vectorial addition of U, would result in C2. Similarly, W3 plus U would be equal to C3. I have also indicated here the absolute and the relative angle with respect to the axial direction. So alpha 2 be the absolute inlet angle and beta 2 be the relative angle. Similarly, beta 3 and alpha 3 be the exit relative angle and absolute angle respectively. Please note here the velocity triangle would be just mirror image to each other, and here alpha 2 must be equal to minus of beta 3 and beta 2 will be equal to minus of alpha 3. Note there, this alpha 2 would be equal to beta 3 and alpha 3 would be equal to beta 2, but they are of opposite sense. So this is with respect to the velocity triangle for a 50% reaction turbine. Now I'll derive the expressions for blade loading capacity with the help of velocity triangle for a 50% reaction machines. Since the velocity triangle here is symmetrical, I can write W theta 2 is equal to C theta 2 minus U. That must be equal to minus C theta 3. Look, W theta 2 and C theta 3, they are in opposite directions. Hence, from here I can write C theta 3 is equal to minus within the bracket C theta 2 minus U. Now, C theta 2 minus C theta 3 would be equal to, putting the value of C theta 3 here, twice C theta 2 minus U. Now, let me define xi, which is the blade loading capacity, equal to C theta 2 minus C theta 3 by U. Put the value of C theta 2 minus C theta 3. So xi would be equal to twice C theta 2 divided by U minus 1. Now from the velocity triangle I can easily show C theta 2 is equal to Cz into tan alpha 2. Thus put the value of C theta 2 in this expression. You will get xi equal to twice Cz by U into tan alpha 2 minus 1. That means xi equal to twice phi tan alpha 2 minus 1. Note that here for a 50% reaction machine, the expression of xi is equal to twice phi tan alpha 2 minus 1, which is given by equation number 8, where the xi for an impulsed machine was twice within the bracket phi tan alpha 2 minus 1. Now, the equation 8, that is xi is equal to twice phi tan alpha 2 minus 1, indicates the effect of nozzle outlet angle on the work output of a reaction turbine. Again, large nozzle angle alpha 2 is desirable, imposing the same limitation as stated earlier, where the typical values of alpha 2 are close to 70 degrees for possible large power output. Furthermore, for a special case of axial outlet velocity Cz, when alpha 3 and beta 2 are 0 and the velocity triangle becomes a rectangle, then the stage work output can be given by xi is equal to 1. Thus, for the same blade speed and for axial outlet velocity, the impulse stage work is twice than that of 50% reaction stage. I like to state here stating that for the same blade speed and for axial outlet velocity, the impulse stage work is twice than that of 50% reaction stage. However, we can expect that the impulse stage to have somewhat larger losses, since the average fluid velocities in the stage are higher than the 50% reaction machines. Furthermore, the 50% reaction stage is not uniquely desirable, of course. One can use any degree of reaction greater than 0 to design a turbine of acceptable performance. Let's continue the discussion, and now I'll derive a relation between xi, phi, and r. The gas flow angles at inlet and exit of blades can be expressed in terms of xi, phi, r. For the rotor blade, the relative total enthalpy remains constant, and hence we can write H2 plus W2 squared divided by 2 must be equal to H3 plus W3 squared by 2. Hence, H2 minus H3 is equal to W3 squared by 2 minus W2 squared by 2. Considering the velocity triangle, I can write W squared is equal to W theta squared plus CZ squared. So putting the value of W3 squared and W2 squared in this expression, I can write H2 minus H3 is equal to W theta 3 minus W theta 2 into, within bracket, W theta 3 plus W theta 2 divided by 2. Considering the definition of degree of reaction from equation 6, now R can be expressed as R is equal to, within bracket, W theta 3 minus W theta 2 into, again within the bracket, W theta 3 plus W theta 2 divided by C theta 2 minus C theta 3. Again, from the velocity triangle as presented here, I can write C theta 2 minus C theta 3 is equal to W theta 2 minus W theta 3. Thus, R can be written as, within bracket, W theta 3 plus W theta 2 divided by twice U, following the earlier equation. Putting the value of W theta 2 and W theta 3 in terms of beta 2 and beta 3, R can be expressed as minus half Cz by U, within bracket, tan beta 2 plus tan beta 3. Cz by U is flow coefficient phi, so R can be expressed as minus half phi tan beta 2 plus tan beta 3. Now we have already proved xi is equal to phi within the bracket tan beta 2 minus tan beta 3. Thus, from equation 10, this and equation 5, I can write by solving these two equations as tan beta 2 is equal to xi minus 2r divided by 2 phi, and tan beta 3 is equal to xi plus 2r divided by 2 phi. So these two are important equation, which says tan beta 2 and tan beta 3 in terms of xi, r, and phi. That is equation number 11 and equation number 12. We have already proved that U over Cz is equal to tan alpha 2 minus tan beta 2, and that also equal to tan alpha 3 minus tan beta 3. Thus, from the geometric relation, I can say tan alpha 2 is equal to tan beta 2 plus 1 by phi, which is denoted by equation number 13, And similarly, tan alpha 3 is equal to tan beta 3 plus 1 by phi, which is denoted by equation number 4. Hence, from the given relation of psi, phi, and r, we can estimate the flow angles and the blade layout. Furthermore, combining the equation 10 and 30, we can show that r is equal to half within the bracket 1 minus phi within bracket tan alpha 2 plus tan beta 3. Both alpha 2 and beta 3 are the exit angle. Thus, r here has been expressed in terms of exit flow angle. Now, for the special case of symmetrical blading, that occur for 50% reaction blading, that we know alpha 2 is equal to minus alpha 3, and hence from this relation you can easily show that in this case, when alpha 2 is equal to minus alpha 3, r becomes half. Furthermore, for another case, when w theta 3 must be equal to minus w theta 2, then r becomes half. Thus, from this relation, I wanted to say that for a special case of symmetrical blading, when alpha 2 is equal to minus alpha 3, we length to r equal to half. Similarly, when w theta 3 is equal to minus w theta 2, r becomes 0. Another very interesting case is that what happens when the outlet velocity c3 becomes axial. When c3 becomes axial, c theta 3 is equal to 0, and it follows that w theta 3 is equal to cz into tan beta 3. That's we get from velocity triangle as indicated here. And hence w theta 3 is equal to minus u. Thus I can write tan beta 3 is equal to minus 1 by phi. Now from equation 15 we get r is equal to 1 minus half phi into tan alpha 2. So this is the expression for r. 1 C3 becomes axial. Furthermore, for zero exit sword, the blade loading capacity becomes, from equation 5, psi is equal to phi into tan alpha 2, since here alpha 3 becomes 0. Thus, for axial outlet velocity, r becomes 1 minus half phi into tan alpha 2, and psi is equal to phi into tan alpha 2. Now equation 16 and 17, that is r is equal to 1 minus half phi into tan alpha 2, and psi is equal to phi into tan alpha 2, have been used in plotting figure 7, which relates to the design condition only. Look, figure 7 represents the work capacity psi and degree of reaction r of axial turbine stage, where exit swirl component is 0. So this is psi-phi relationship for different values of r and for different stator outlet angle alpha 2. What it shows that for a given stator angles, the impulse stage requires a much higher axial velocity ratio than that of 50% reaction stage. That means, look here, suppose, let's consider alpha 2 is phi, alpha 2 is equal to 70 degree. So for 70 degree, if we consider the stage is an impulse stage, so it will have a phi which is about 0.6. However, if we take a 70 degree stator outlet angle and degree of reaction is 0.5, then phi would be around 0.3. So thus, from this plot, it is very clear that impulse stages require much higher axial velocity ratio than that of 50% reaction machines. Thus, in the impulse stage, all flow velocities are higher, and that is one of the reasons why the efficiency is lower than that of 50% reaction stage. In this lecture, I have discussed on degree of reaction and also derived the expression for blade loading capacity of impulse and 50% reaction machines. Furthermore, I have discussed about the implications of exit nozzle angle and the relation between xi, phi, and r. Thank you for listening.